calculus students. I'm Mr. Jensen. Some of you guys are my current students, and some of you guys are now with Mrs. Martinez, and I haven't seen you in a long time, but I'm back. So as Mrs. Martinez explained to you guys, all of you guys hopefully, she's already worked through an example yesterday on one of these problems in regards to differential equations and slope fields. My plan is to do the videos on day 2 for the edge elastic problems, and so that you have just another explanation of another teacher showing it to you. So without further ado, here we go. I'm going to get into it. The problems you guys had today, so we had to consider this differential equation. dy dx is equal to 2y times x plus 1. And on that, it's asked us to do 4 different things. It's asked us first in part A to create a slope field. This is by far the easiest part of all of these problems. Creating a slope field literally means, for all 12 points on here, means we need to put in the x and the y value here and determine what our slope looks like. Just a quick reminder that this is 0 slope. This would be undefined slope. This slope is positive, like a positive 1. This would be like a positive 1/2, and then this is like positive 2 or positive 3. It's a really steep line. If we go back to 0, a negative slope would be going downhill, so like -1, and this would be like -3, and this would be like -1/2. So with that said, what I like to do is I just start by picking a point. Usually when I'm doing my slope field, I'm going to pick a point, like maybe I try the point 0, 0, and I'm going to put 0, 0 in for x and y here. That means that dy dx would equal 2 times, let me get out of the way, 0 times 0 plus 1. I'm putting in 0 in for x and 0 in for y. When I do that, I got 0. 2 times 0 is 0. 0 plus 1 is 0, but because they're all multiplied, it's 0. So that means my slope at 0, 0 is 0. So at this point right here, we should have a flat line kind of looking like that. We're just showing like a small version of what the slope would look like. Quickly, what I can identify then is I'm looking for ways that will make this faster. What I notice is that if my y value then is 0, that's going to be 2 times 0, and 0 times any number will just be 0. So I think everywhere that the y coordinate is 0, I'm going to have a flat line here and here. As I work through it, now I need to do the other points. Let's try this point here. That's the point 0, 1. When I do 0, 1, again, I'm putting that into the equation. 2 times my y value times something plus 1. My y value here is 1. My x value is 0. So 2 times 1 is 2. 0 plus 1 is 1. And so I get 2. So my slope at 0, 1 is 2, which should be kind of a steep uphill line. Something like that. As we work our way through, I'm going to continue doing more and more points and hopefully filling out more and more of this table here. I'll try the point 1, 1. And I get 2 times 1 times 1 plus 1. I got 2 times 2. I got that to be 4. Something like this. Even steeper than that. It's hard to show, and that's okay. If I try another point, let's say like -1, 1. That would be this point here I'm trying to find the slope for. That would be 2 times my y value, 1, and then -1 plus 1. When I do that, 2 times 1 is 2. -1 plus 1 is 0. That's going to be 0. And so at -1, 1, I got 0. And then really quickly then I realized, oh, if I put x is equal to -1, that's going to make this number 0. So anywhere x is -1, that's going to give me a 0 slope here and a 0 slope here. All that does is it makes my process of doing this go a little bit faster. Now I only have 1, 2, 3, 4 points left to check and find those slopes for those. I'll go ahead and do 0, 2. When I put that in, I got 4 times 1, so I got 4. When I do the point 1, 2, I got 2, and then 2 times 2 is 4. That's going to be 8, so that's almost straight up and down. And then down here, this is the point 0, -1, so that's going to be -2. so that should be a downhill looking line. And then at 1, -1, that's 1 is going here, so 2 times -2 should be done like this. So this is what you should get something like for your slope field for part A. Okay, so we finished part A, and now we're moving on to part B. Part B says that when x is -1 and we're in the second quadrant, they want us to show that this creates a relative minimum for this particular solution. We know that we're working with the derivative, so we get a critical value, a possible max or a min, when we put in x is -1 and we get a 0. So first thing I want to check out is what makes it 0. And notice that if I put dy dx equals 2y and I put in -1 for x, and if I don't know what the y value is, I get -1 plus 1 is 0. 0 times 2y is 0. And so the dy dx is equal to 0. So that means that we have a possible critical point there. We need to prove that it's a minimum. The way that we can prove that it's a minimum is by taking the derivative of dy dx, go to the second derivative, that's y double prime. And y double prime, the second derivative tells us about our function's concavity. So remember that when the second derivative is positive, our graph would be concave up. And when when the second derivative is negative, that tells us that our graph is concave down, so opening down. So we want to find the second derivative of this. So if I take dy and dx equals 2y times x plus 1, and we want to take the derivative, we want to take d dx of this. Okay? As I do that, the derivative of the first derivative, this is going to be y double prime, or you can write it as d squared y dx squared. If you don't like how that looks, you can just write y double prime. It means the exact same thing for us. And then here we're taking the derivative. This is going to do two fun things for us. The first fun thing is that it lets us do implicit differentiation, because we're taking the derivative of y terms in terms of x. So that's going to create that dy dx fun stuff. In addition to that, we have the product rule we're going to apply. So let's go through it. As I take the derivative of this, this is my first term, this is my second term. So my first term here, I'll take the derivative of this first. That would be just 2, but because it's y stuff, it's going to create a dy dx term times the original x plus 1 value here, plus, this is now the product rule, the first term, 2y, times the derivative of the second term, which is just 1. Okay? So we use product rule. We can try to simplify this a little bit. This is going to be 2 times x plus 1 times the dy dx plus 2y. Dy dx is all of this fun stuff. So I can put all that fun stuff in here. So that's going to be 2x plus 1. I substitute in dy dx, so that's going to be, let me write it in blue, 2y times x plus 1. It's too big. I'm running out of room. Sorry. So that's my dy dx plus 2y. I can simplify this a little bit. Let's see if we're doing it right. It should be 4y times x plus 1 squared plus 2y. So now we want to say, this is our second derivative. So we did all this work to get the second derivative. Now we want to say, okay, the goal was originally to prove that we have a minimum when x is equal to -1. And we're in the second quadrant, which will be very important. Us being in the second quadrant, that will basically tell us that the y values are also positive. Okay? So when we do this, then, when x is equal to -1, what we're able to get then is that the second derivative, y double prime, is equal to 4y times -1 plus 1 squared plus 2y. -1 plus 1 is 0. 0 squared is 0. 0 times 4y is 0. So all of this term goes to 0. And so the second derivative is equal to 2y. Well, why is this important? If the second derivative is equal to 2y whenever x is equal to -1, and because we're in the second quadrant all the y values are positive, that means that our second derivative, y double prime, is always going to be greater than 0. If our second derivative is greater than 0, that means my entire graph is going to be concave up during this time. When my graph is concave up, it means that my function is going to have a minimum. So let me write that down. Since y is greater than 0 and dy dx equals 0 when x equals -1, comma, and y double prime is greater than 0, then we have a relative minimum. Proving what we were trying to go. And this then completes our second part, part B, when x is equal to -1 and we're in a second quadrant, that we have a relative minimum. So we've done part A and we've done part B, we're working on part C. For part C, they've asked us to find y equals f of x for satisfying this initial condition. Basically what they're asking us is they've given us the derivative, they want us to find the integral. Notice when we normally integrate, we get that plus c, the constant of integration, but we're able then to find what c is using these initial terms. Notice this is f of 0 equals 2, which may have been slightly different than the original problem at some point. Hopefully it's been edited by now, and this is what you've seen, is that f of 0 is equal to 2. So what we're going to do is we're going to integrate this term right here. In order to integrate this, what we need to do is we have dy dx is equal to 2y times x plus 1. In order to integrate this, what we need to do is we need to separate our x variables and get them on one side of the equation, and our y variables, we need to get them on the other side of the equation. To do that, we need to get the dx over there, and with all the x terms, and we're going to take the y terms and bring them over here. We simply multiply dx over, and so I get dy is equal to 2y times x plus 1 dx. And the y terms, I need to bring these y terms over here. So I'm going to divide by, in this case, I'm just going to divide by the y. When I do that, because these are all being multiplied, I get 1 over y dy equals 2 times x plus 1 dx. This 2 can distribute in, and it'll make it a little bit easier for our integration purposes. And so we'll do that soon. But as we go to integrate this now, as I go to integrate the left side, the integral of 1 over y is just going to be natural log of absolute value of y plus c equals, here, if I distribute the 2 here, this would have been 2x plus 2 dx. Maybe I should write that, I guess I'll write that, the integral of 2x plus 2 dx. And then we integrate this. So I still have natural log of absolute value of y plus c equals, the integral of this, integral of x is, of 2x will turn into just x squared, plus integral of 2 goes to 2x, and then we have a plus c. At this point here, our goal is still to solve for y. So we need to get it by itself. The first thing I would do is subtract over a c, but notice these are constants of integration. So this c and this c are different values. But the cool part is, when we do c, which is some number, minus another c, which is another number, it just turns into c. And so I'm going to write this up here. And we should get, then, natural log of absolute value of y equals x squared plus 2x plus c. The next thing we want to do, then, is we want to get y by itself. So we're in log form. Now you got to go back in your days to going from log form to exponential form. remember that if I have like log base b of, let's do y equals x, that the way that I change this, I would swoopy-doop back in our pre-calc days, or however you learned it in your IM3 days. This would be b raised to the x equals y. And this is how we would change it from log form to exponential form. Here, for natural log, my base is e. So as I swoopy-doop and change this, this becomes y equals e raised to the x squared plus 2x plus c. You'll notice that when I changed it from log form to exponential form, I no longer need the absolute value bars because I'm no longer dealing with the restriction of natural log. In addition to that, this e raised to any number here is always going to be positive. At this spot here, we can do one more kind of creative thing to solve for this c here. With exponents, if these are all being added, this is the same as y equals e to the x squared times e to the 2x times e raised to the c. Notice that when we have exponents, remember our rule normally with exponents is that if we have a common base, we would add exponents. And so we're used to going from this stage, going up to this stage. The reason that we break it down this way is because here you could identify that if I have e, which is a number, raised to some constant, which is a number, this is just all going to create a brand new c value. When I do that, this becomes y equals, and I'm going to put that c value in front, times e, and then I can combine these two back as x squared plus 2x. The reason I do that is this makes this a lot simpler to substitute in and to find my value of c. Solving for c as an exponent is much more difficult than solving for c here as a constant being multiplied. Now I'm ready to take my initial condition, f of 0 is equal to 2, and put that in here. So x is 0 and y is 2. That would be 2 equals c times e raised to the 0 squared plus 2 times 0. And so I get 2 equals c times e raised to the 0 squared is 0, plus 2 times 0 is 0, 0 plus 0 is 0. E raised to the 0 is like anything with 0, that's just 1. And so I get c is equal to 2. At this spot now I can write my final answer, putting 2 back in for c, and so I get y is equal to 2 times e raised to the x squared plus 2x, giving us our answer here to part C. Alright, so we're back. So far now in the problem we've done part A, part B, and part C. We're now ready to go to part D. Part D says using your answer from part C, we're going to find the limit as x goes to 0 of f of x minus 2 all over tangent of x squared plus 2x. This seems very intimidating as it's a big term here. Our answer from part C was that f of x or y is equal to 2 times e raised to the x squared plus 2x. So we can substitute that in there for f of x, and that means I get the limit as x goes to 0 of 2e to the x squared plus 2x minus 2 divided by tangent of x squared plus 2x. Going back to your limit days, the first thing we want to try when we get a limit is we just want to try putting the number 0 in. So when we put the number 0 in here, 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 and here, we would get, this will end up giving us 2 times e raised to the 0 squared plus 2 times 0 minus 2 divided by tangent of 0 squared plus 2 times 0. So we're putting in the value 0 here. 0 squared is 0, plus 2 times 0 is 0. E raised to the 0 is 1. And so I get 1 times 2, which is 2. So that would give me 2 minus this 2. Divided by, down here, 0 squared is 0, plus 2 times 0 is 0. So this is tangent of 0. Tangent of 0 is y over x at 0. Remember, that's the point 1 comma 0. So that would be 0 divided by 1. 0 divided by 1 is 0. So this is going to be 0. So this is going to be 0 over 0. So what this tells us is that when we try direct substitution and putting in 0 in here, we got 0 over 0. Which means now we're allowed to use L'Hopital's rule. And using L'Hopital's rule, we're going to take the derivative of the top and the derivative of the bottom, and then we're going to substitute it in again, hoping that it will work out. So let's go for that. This is the same thing then as using x goes to 0. Now we got to do the derivative of the top. The derivative of the top, we don't have to use product rule because this is a constant. I do have to take the derivative of this. The derivative of e to the x is just e to the x. I will have to use chain rule here. So this is going to be 2 e to the x squared plus 2x times, using the chain rule, the derivative of x squared plus 2x is 2x plus 2 minus 2, but the derivative of 2 is 0, so that's going to go away. And down here, we have to do chain rule again. Derivative of tangent is my outside function, and derivative of tangent is secant squared of the original x squared plus 2x times chain rule. I need to take the derivative of the inside function. The derivative of the inside function will be 2x plus 2. So we hopefully successfully did L'Hopital's rule here. Now we're going to substitute 0 back in and see if this works out this time. Thankfully, because I did it ahead of you, it's going to. Let's see though. When I put 0 in here, I get 2 times e raised to the 0 squared plus 2 times 0 times 2 times 0 plus 2. And then in the denominator, I need to put 0 in down here. So I should get secant squared of 0 squared plus 2 times 0 times 2 times 0 plus 2. When I go after this now, I need to simplify all this fun stuff and try to get up a number here. 0 squared is 0, plus 2 times 0 is 0, e to the 0 is 1, 1 times 2 is 2, so I get, in the numerator here, I got 2 times 0 is 0, plus 2 is 2 more, so it's going to be 2 times 2 in the numerator. In the denominator down here, 0 squared is 0, plus 2 times 0 is 0, secant squared of 0. Remember, secant is 1 over my x value, or 1 over cosine. The x value at 0 radians is 1. And so secant is 1 over the x value, so 1 divided by 1 is still 1. And then I got to square it, so that's all still 1. Times, over here, 2 times 0 plus 2 is 2. And this will give me then 4 divided by 2. Which this goes to 2. So the limit of this, after using L'Hopital's rule, is 2. At this point, we can take a deep breath, let it out. Hopefully we're able to solve parts A, B, C, and D. As I am new at teaching on a whiteboard, online, or through like a remote system, if you guys could do me a couple favors for feedback from me. First thing, right below there, if you give me a like, a big old thumbs up. And then second, if you would put a comment, either saying, hey, I get it, I'm totally understanding it now, or hey, could you re-explain part C? I was really confused when you made this move. Some of that stuff would really help me out. I hope you guys have a great day, and I'll see you guys in a couple.